Right, at the feedback session, we were asked to look at a adiabatic CSTR. What we were asked to do is, let's consider, as I said, a CSTR. We'll look at a liquid phase reaction, A goes to B. Now, liquid phase, basically when you read that, what it's telling you is the reaction is constant density, and that implies the volumetric flow rate in and out the reactor is constant. We assumed that the reaction was elementary. So if we have a look at the reaction A goes to B and the reaction is elementary, the rate then is minus K Ca. The temperature dependence is in K, and typically the rate constant is given as minus K naught e to the minus E over RT. So that would be our rate equation, and there is where temperature would influence the rate. We said we were going to have a feed of A, an inert, and what I've assumed is that the molar flow rate of A, the reactant, and the inert is the same at N naught. We said that there was going to be a 50% conversion of A across the reactor. In other words, on the output stream, if you think of what the definition of conversion is, and please don't try and memorize formulas, try and derive them from scratch. I always do that because otherwise you make mistakes, you choose the wrong formula. It's got an assumption in that you didn't have, that's not valid for your case. And when I'm marking, I always give marks for derivations. So the definition of conversion, XA, is it's the molar flow rate in minus the molar flow rate out divided by the molar flow rate in. In our case, and that must be equal to half, we can then rearrange that equation, and that says the molar flow rate out of A is a half N naught. We can also then work out what the molar flow rate of B out is, because remember, whatever B we formed is from A used up, which is Na naught minus Na, and that is just, Na was just a half N naught, and so the molar flow rate of B is a half N naught, which is the same as the molar flow rate of A leaving. Now, let's just have a look at a picture of what we're talking about. There's our reactor. Our flow rates in, Na naught is N naught, and the same as inert. The inert entering the reactor must be the same as the inert leaving, so the same flow rate N naught of inert must be leaving. Na and Nb out must each be a half N naught, as we showed. Now, other thing we needed was the concentration. You have Ca, and remember the definition of concentration is molar flow rate divided by volumetric flow rate. So Na would be the volumetric flow rate. And remember, the CSTR, all the material in here has the same concentration as the exit. And so if we're working out the concentration in the reacting area, it's the same as the concentration in the exit, which is the molar flow rate divided by Q. And the molar flow rate is a half N naught divided by Q, and we can call that a half C naught if we like. Right. If we look at the equation for the CSTR, the equation for the CSTR says that, and again notice I do it from scratch, the molar flow rate in plus the moles of A formed must be the molar flow rate of A out. Now the molar flow rate of A in is N naught. The rate equation we've written over here, so I'm just putting that in, and the molar flow rate of A out is a half N naught, as we've said here. I can divide both this equation by the volumetric flow rate. N naught divided by Q is C naught. There's my rate equation with the temperature dependence in, and that's N naught divided by Q is then C naught again. And combining the two C naught terms here, I get a half C naught, and taking that to the other side is K naught e to the minus RT over tau. Now what is interesting is if I'm given a value for C naught, K naught, all the system constants, I could work out the residence time of the reactor if I knew the temperature. And that is why I need the energy balance. So we now need to look at the energy balance. And to keep it simple, what we're going to assume in the energy balance is that the Cp of the reactants A and B is the same, and which is also the same as the inert, and we're just going to call that Cp. Right, so the next step is the energy balance. Now the energy balance for an adiabatic system says the enthalpy entering of the stream entering must be the same as the enthalpy of the stream leaving. So if this stream comes in at T naught, that stream maybe leaves at temperature T, and we're trying to calculate what that temperature T is. How do we calculate enthalpy? Well, the general form is enthalpy. When you have a mixture, it's the sum of the molar flow rates times the enthalpy of the pure components of each of the components. And so, for example, if for our feed stream of A in inert, the enthalpy in would be the molar flow rate of A in times the enthalpy of pure A at the inlet conditions times plus the molar flow rate of inert times the enthalpy of inert at the inlet conditions. Now, how do you calculate enthalpy? Well, the enthalpy is the enthalpy of formation plus the integral of Cp dt between the reference conditions and the stream temperature. If Cp is constant, this simplifies to just simply the sum of the enthalpy of formation plus Cp of the component times the temperature difference. But that only is true if Cp is constant. We said we were going to assume that, and so then I've rewritten that's the enthalpy of A in as the formation of A plus the Cp of A, and then we add in, because the molar flow rate in our case of the A in inert is the same, I've taken it out constant, and that's the enthalpy of the inert. And I've combined these two terms, the Cp terms, because we said that the Cp we're going to assume is the same. So that is the enthalpy in. Right, similarly we can work out the enthalpy of the outlet stream, in other words that stream. It's the sum of the molar flow rate of A times the enthalpy of A at this temperature that we're trying to work out, the flow rate of B times the enthalpy of B, and the same with inert. I've substituted in, the half comes in because Na is a half N naught. That's the half because of the molar flow rate is only a half N naught. There's the flow rate for B, or the enthalpy for B, and that for inert. We can now equate the enthalpy in and out, because we said for an adiabatic system they must be the same. So I've equated that to that term, and so this is what the equation looks like. I've changed the Cp of inert. Remember, we could just say it's the Cp, and so that is the term, and we can now look at simplifying that further. Right, I can then look at my terms and combine. What I've combined is the Cp terms and the enthalpy of formation terms. If I look at the Cp terms, I can see that I end up subtracting those two terms to get 2 Cpt in, the difference between the temperature in and out. I also then have a difference in enthalpies of formation, and the difference in enthalpy of formation is what we commonly term the delta H of reaction. So if I rearrange that equation, I get the change in temperature between the feed and the exit is equal to the ratio of delta H of reaction over Cp, and if I combine the constants in front, it's a quarter of that. And so this is the relationship, or tells me what the temperature at the exit would be. I can then substitute that back into my CSTR equation, which I've done over here, and there's that temperature dependence. And so that says if I know all my system constants, my concentration in, my rate constant, the first one, the K naught, activation energy, I can then, and my delta H of reaction and Cp, I could then work out all of those terms which would allow me to calculate the residence time.